Namaste children, welcome back again to this virtual class. In today's session, we are going to start a new chapter under physics of your class 9, that is work and energy. Prerequisite for work and energy we have already completed. What are those? Motion we have completed, and cause of motion also we have seen, right? Force and loss of motion. We have learned that whenever we apply force, then the object starts moving. So we have found out that it is force which causes motion. So we have completed the chapter motion and the laws of motion. This will help us to understand the concept of work. Now, in our day-to-day life, we apply force. With the help, when we apply force, then the object starts moving, right? We have learned that it is unbalanced force which causes motion to an object. Whenever we apply force to an object, if the object moves, then work is said to be done on that particular object. For doing work, energy is required. For example, we do several kind of works, right? In order to do work, we use our muscular force. The muscular force is coming out from the energy. So we need energy to apply force, right? So with that energy, force is created, force is generated. With that applied force, the object starts moving. Similarly, a horse pulling a cart also requires energy. With that energy, force is applied. With that force, the cart is being pulled. You are much familiar with vehicles and all, right? Vehicles also move by when the engine works. This engine requires force. This force is applied from energy, and this energy is obtained or provided by the fuel. So, presence of the fuel in the automobile gives energy. With that energy, force is applied. With that force, the object is moving. This is what the basic thing about the work done. You are much familiar with work, right? From the morning to evening, you used to do various physical activities which we considered under a work. When you go to school, teachers used to tell that students work hard so that you will get good marks. After coming back to home, your parents put pressure on you to work hard so that you will get more marks. So all these we considered under a work. In ordinary language, the meaning of work is something attached to physical and mental activity. But in physics, it has only one meaning. What is that? Work is said to be done on an object if the applied force produces motion. What does it mean? Suppose when an engine moves a train, then the engine applies force on the train. As a result of this, the train moves along a straight line, right? Here we see work is done on the engine. As a result of this, the train has moved. Similarly, we see another example. A horse is pulling the cart. While pulling, the horse has to apply its force, right? While applying force, the cart starts moving. Here also, work is said to be done on the cart. Since the applied force by the horse moves the cart. When we apply force to an object, the object moves. At that time, what happens? We are applying our force. Muscular force is being applied on the object. As a result of this, the box moves. Here we can say that work is done on the object since the applied force causes motion to the object, right? So this way we can understand the work in physics. Now we see another example while climbing on a staircase. Can we consider it as a work done? Yes, children, it can be, because here we know that earth attracts every other object towards itself. Now, when we climb over the stairs, we are moving our legs against the gravity. So, force is being applied in order to climb the stairs. So, we can say that force is applied. As a result of this, our legs get lifted. So, this is also an example of work done. So, this way we can understand work done. Whenever we talk about work done, it is just the applied force and the displacement or the distance covered or the motion takes place. Here on, whenever we talk about motion, then it must have some applied force. As a result of this, the object would have traveled some distance or some displacement. Now we discuss about the factors on which the work done depends. Work done by a force on a body depends on two factors. They are, one is magnitude of force, second one is distance through which the body moves. Now we see magnitude. If the applied force is more, then the work done will be more. Suppose if 100 Newton of force is applied on an object and which causes motion, then there must have some distance covered, right? If we apply 200 Newton of force, then definitely it would cover more distance. So from this we can understand that the work done by a applied force depends upon the magnitude of force. If the magnitude of force increases, then work done on the object will also increase. Now we see the second factor on which work done depends. The second factor is the distance through which the body moves in the direction of force. Suppose if we are applying force on an object and it covers, for example, 10 meter of distance, and by applying force another object moves 20 meter of distance in the direction of the applied force, then the object which covered 20 meter distance will have more work done. So by the distance through which the body moves in the direction of force decides the work done on that particular object. So these are the two factors on which work done by a force on a body depends. Got it, children? On the basis of what we have learned before, we can define work as work done in moving a body is equal to the product of force and the displacement or the distance. Mathematically, it can be expressed as W is equal to F into S. Here W is the symbol of work done, F is the symbol of force, and S is the displacement or distance covered. So this way we can understand what is work. Let us now understand the unit of work done. We know that work done is the product of force and displacement. So W is equal to F into S. By substituting the SI unit of the force and displacement, we will get the unit of work done. So here work done is equal to, we know that the unit of force is Newton and the unit of displacement is meter. So work done will equal to Newton meter. So the unit of work done will be Newton meter. Here the unit of work done is joule. When a force of 1 Newton is applied on an object which causes motion to a distance of 1 meter in the direction of applied force, then we say 1 joule of work is done on that particular object, right? So this way we can understand the work done on an object. Now one important thing to note here is that the applied force must cause motion. Here motion means it must cover some distance. If applied force does not produce any displacement or cause any motion, then zero work is done on an object. Now let us take an example. Suppose you are pushing a wall. When you push the wall, you are applying whole of your energy and whole of your force is applied and forcefully you are pushing the wall. Will the wall move? The wall will not move, right? Here substitute the values here, then what will be the work done you will come to know. Here F is equal to force into displacement, right? Force, whole force, whatever the muscular force, everything you applied. For example, say for your 500 Newton force is applied on that wall to move, make the wall move, and the wall did not move at all, right? The displacement will be 0. Apply the value here. What will be the work done then? Work done is equal to 500 Newton multiplied by 0. Then the entire work done will become 500 multiplied by 0 is 0. So here we have applied, when you apply force on the wall, you yourself get exhausted and work is done on you, because while applying force, whole energy gets exhausted and the blood rushes to the muscles to cause force. The work is done on you, but the work is not done on the wall, because all the force applied on the wall did not make the wall move, right? So here zero displacement we could see. So the work done on the wall will be 0. So you always keep in mind. Now we learn work done against gravity. We know that Earth attracts every other object towards itself with some force. We call it as gravitational force. We will also call it as weight of an object, right? Now, in the beginning of the video, we have discussed about while climbing on a stair, we are moving our legs against the gravity, right? So when we do activity, when the work is done against the gravity, then the formula W is equal to F into S will not come into play because here the work done is against the gravity. We know that Earth is attracting every other objects. Now we are lifting our body or any object is lifted above the gravity, then it is the opposite to the direction of the applied force. There against the gravity work has to be done. In such case we use W is equal to mgh. Here W is the work done which is equal to mgh. Here m is the mass, g is the acceleration due to gravity also known as gravity, h is the height to which the object is lifted. Based on this, let us do some numerical problems.
Now look at the question. How much work is done by a force of 10 Newton in moving an object through a distance of 1 meter in the direction of the force? Here we need to find work done. The quantities given are F is equal to 10 Newton, distance is given as 1 meter, and we have to find work done, right? We know that work done is equal to the product of force and displacement. Here you substitute the value of force and displacement, then we will get 10 into 1, which will be 10 joule of work will be done, right? Very easy question, right? Let us see another numerical problem. See the second numerical problem. Calculate the work done in lifting 200 kg of water through a vertical height of 6 meters. Here assume that the value of G is given as this, right? Here the work done is against the gravity. We know that for finding the work done on an object which is against the gravity, then we will use the formula W is equal to mgh, right? Here mass is given as 200 kg, right? G is given as 10 meter per second square, and height is given, h is given as 6 meter. Substitute the values, straight away we will get. So m is 200 multiplied by g is 10 multiplied by height is 6 meter. So work done will be 12,000 joule, or we can write it as work done is equal to, we know that 1000 joule is equal to 1 kilojoule, right? So here divided by 1000 will get 12 kilojoule of work will be done. Very easy, right? Let us see another numerical problem. Now see this question. A car weighing 1000 kg and traveling at 30 meter per second stops at a distance of 50 meter, decelerating uniformly. What is the force exerted on it by the brakes? And also you have to find what is the work done by the brakes, right? Now in this question, look very carefully. First quantity that has to be found out is force. In order to find the force, we need acceleration. We know that F is equal to ma. So mass is given in the question, but acceleration is not given, right? Here acceleration could be found out from the values given here. You see, initial velocity, final velocity is given, right? So with these values we can easily find the acceleration. So in order to solve this numerical problem, firstly we need to find the acceleration. So here initial velocity is given as 30 meter per second, and here final velocity will be 0 meter per second, since here the car stops at a distance of 50 meter, covering 50 meter distance, right? So stop means the final velocity becomes 0. So here distance is given as 50 meter. By using these values, we can find the value of acceleration by using the third equation of motion, that is 2as is equal to v square minus u square. Here we need to find a, right? So here on rearranging this equation, we will get a is equal to v square minus u square divided by 2s, right? Substitute the values on this expression. A is equal to v is 0, so this will be 0. U is 30 meter per second, so this will become 30 whole square divided by 2 into distance is here 550, right? Upon solving this, we will get minus 3 3s are 9 divided by 2 5s are 10. So this gets cancelled. So here acceleration will be minus 9 meter per second square. Here the minus sign indicates that the acceleration produced is negative, or we call it as retardation, right? Now with the value of acceleration, we can easily find the value of the force exerted, right? We know that force is equal to the product of mass into acceleration. This is what we have learned in the Newton's second law of motion, right? So mass, we have 1000 kg, so we will write here 1000 into acceleration. Just now we have found out as 9 meter per second square. Upon solving this, we will get minus 9000 Newton, right? Once again we got minus. This minus sign indicates that the force applied will be in the opposite direction. That means the brakes are applied. As a result of this, the motion takes place in opposite direction, right? So the direction of motion and the applied force are in opposite direction. This way we can understand the minus sign here. So minus 9000 Newton of force will be exerted by the brakes. Now the next quantity we need to find is work done. First thing we have found out, right? Secondly, we have to find work done. In order to find the work done, we know that the formula of work done is W is equal to F into S, right? Here we know that force we have just now found out 9000 Newton. Here minus sign we should not write. Minus sign indicates the direction of the force exerted. That we should not write. We have to take the force exerted by the brakes. So force will be here 9000 multiplied by, and the displacement is 50, right? Upon solving this, we will get 5 nines are 45. So here 45 0,000 joule. In short, we can write it as 4.5 into 10 to the power 5 joule. This way you can solve this numerical problem. What is, children?
Hope you understood the numerical problem. Let us now learn work done by a force acting obliquely. Now look at the picture. A child is pulling a toy car. Here you see the child is pulling the toy car, and the applied force and the motion of the object, if you see, the motion of the object is not in the direction of applied force. Or we can say that here the applied, all the force is not involved in pulling the car.
Let us understand this in detail. So far we have considered only that case of work in which the body moves in the direction of applied force. That means if force is applied on this direction, then the object will move with the direction of the applied force. But this is not always so. In many cases, the movement of the body is at the angle to the direction of the applied force, as in the case you can see. For example, in this case, when a child pulls a toy car with a string attached to it, the car moves horizontally in this direction, right? But the force applied by the child is along the string in his hand, making some angle, right? So here it is the angle mentioned with the theta. This is, here the car moves along a straight line, that is O to X, but the force is being applied along the string OA. This direction force is applied, but the car is moving horizontally, that is with the direction of OX, right? Thereby making an angle theta, as you can see here. We have learned that work done is equal to the product of force and distance, right, or the displacement. But in such case, we cannot use to find work done by using F into S, since the motion of the object is not in the direction of the applied force. The whole of the force is not being used in pulling the toy car. Only its horizontal component along the ground is the effective force. So we have to understand the effective force. When the force is applied in the earlier case, the motion of an object is in the direction of the applied force. In that case, all the force will be acted on the object to move the object. So the effective force is the entire force applied by us, whereas in this case the effective force is only the horizontal component of the force which makes the toy car moving in a direction. Now we will derive a formula for the work done when the body moves at an angle theta to the direction of the force. How to do? Let us see. Suppose a body lying at point O, this is the point, the object is here, is being pulled by a man. Now though the body is moving on the horizontal floor, this is the horizontal floor, and reaches point X up to here after covering a distance S, but the force is being applied in the direction of OA. So here it is the force, the direction of applied force, but the object is moving in this direction, thereby making an angle. Here we take the angle between the applied force and the motion of the object as theta. Now here you can see very well that the applied force is in this direction, and here in this case only horizontal component of the force which makes the object move in the direction, that is horizontal direction, will be the effective force. So we can say that in this case all the force F is not utilized in pulling the body, only the horizontal component of force F is the effective force which is pulling the body along the ground. Thus the work done in pulling the body will be equal to the product of horizontal component of its force and the distance moved by the body. In this case the horizontal component of force is F cos theta, here theta is cos theta. So here we can write as work done is equal to force of the horizontal component can be represented as cos theta and distance moved by the object S. Here we write cos theta. Why do we write cos theta? Here instead of cos theta we would have used sin theta, tan theta and some other trigonometric functions. Why we only consider cos theta? Dear students, just you see here, it is the direction of motion of the object and this is OA is the direction of applied force and the theta is the effective force. In order to find the effective force, here you see this is the base of the triangle. If you extend it, we will get a triangle, right? So here it is a right triangle. Here the theta is the base divided by the hypotenuse. We know that base by hypotenuse is equal to cos, right? Therefore, in order to find the effective force, we use cos theta. Here F cos theta is the effective force which makes the object move horizontally. So work done will be F cos theta into S. Here theta will give you the angle. So this way we can find work done by an applied force acting obliquely, thereby making some angles. Understood, children?
Let us now learn work done when the force acts right angle to the direction of motion. Just before, while solving numerical problems, we have seen that when force is applied obliquely to the direction of motion, then the formula W is equal to F cos theta into displacement will be used to solve, right? To find the work done. That will give you the net work done on the object. Now, based on this, let us see some of the examples. If the force acts right angle to the direction of motion, what happens? What will be the work done about that? We will see. Here 90 degrees. So force, suppose 100 Newton force is applied. So in the place of force we write 100 Newton. Cos, here theta is 90 degree. Right angle means it shows 90 degree, right? So cos 90 degree multiplied by displacement. Displacement we can take 10 meter, 20 meter, whatever, some positive values we will take. Now here one thing to note is that cos 90 degree, the value of cos 90 is 0. So when cos theta is 0, then the whole term gets 0. So the net work done will be 0. So the force acts right angle to the direction of motion, then the work done will be 0. Let us take some of the examples. Suppose a man is carrying a suitcase or a heavy load is carried on his head and he is walking 100 or 200 meters of distance. How much work is done on the load which he is carrying? 0 work done. Although the object caused motion, although the object covered some distance and force has been applied against the gravity, but the net work done on the heavy load is 0. This is because the man is moving this direction and the gravity, the force is applied above and the object is moving towards this direction. Here you can see that the direction of motion of object is not in the direction of applied force. Here the force is obliquely entering from an angle, thereby an angle is there. This angle is right angle. So by substituting the values in the equation W is equal to F cos theta displacement, then here you will find that it is 90 degree. So the net work done on the object will be 0. One more example we will see. You are carrying your school bag on your shoulder and walking to a distance of 1 kilometer. How much work will be done on your school bag? If such question is asked in your examination, then what will be your answer? Here the work done on the bag will be 0, because although the bag has moved from your home to school or bus stand, but the motion of the object and the applied force makes an angle. What is that angle? Right angle. Whenever there exists force right angle to the direction of motion, then that time the work done on the object will be 0. This you always keep in mind, children. Now we discuss work done when the force acts opposite to the direction of motion. We are very much familiar with the fact that when the ball is kicked, the ball will move along a straight line. After traveling certain distance, then the ball stops. Why does the ball stop? Because we have reason for this. We have already discussed in the previous chapter, right? It is frictional force. When the ball is rolling down the ground due to applied force, after some time the ball slowly decreases its speed. This is because the frictional force is acting opposite to the direction of motion. So here the work is done due to the frictional force, right? The applied force causes motion towards the reverse direction, right? Here the work is done in the opposite direction. In such case, the value of work done will be negative. Dear children, so far we have learnt much about work. Whenever we talk about work, the work done may be positive, work done may be negative, work done may be 0. The work done will be positive if the applied force causes motion in the direction of applied force, then the work done will be positive. If the applied force and the direction of motion is in opposite direction, then the work done will be negative. If the applied force on the object is making a right angle, then the work done will be 0. So these three things you always keep in mind while learning work done. So dear students, we have come to the end of this topic, work. Let me ask one question. What will be the work done by the earth on the satellite which revolves around it? Whether it is 0, positive, negative, that you have to answer. Dear children, work done by the earth on the satellite around it in a circular path is 0. How come this 0? We have already discussed in the previous chapter about the uniform circular motion. Let us have an idea and try to understand how the work done is 0. See here, the uniform circular motion, at each point it changes direction, right? Now here the satellite is moving around the earth by means of centripetal force. That means the satellites which revolves around the earth is with the help of centripetal force exerted by the earth, right? Now here the centripetal force is the radius of the earth, we can say. So if you see the angle between the tangent and the radius, it makes an angle of right angle, right? So here we know that the work done by the earth on the satellite will be found out by using the formula work done is equal to F cos theta into S. Here motion is there, some displacement we can see, force is centripetal force, but the cos theta will be 90 degree. So 0, so anything multiplied will be 0. So the work done by the earth on the satellite will be 0. Hope you understood how it becomes 0. So dear students, that's all we have for today. Hope you understood today's class. So with this I would like to conclude. Before concluding, I would like to give some easy home assignments which you can practice at home. So here is your home assignment. Hope you will find all these home assignments very easy. See you all on another day. We will be learning about energy. So be energetic. Till then, keep learning. Take good care of yourself.